Today we will see the importance of arrays in programming, and we will understand how they serve as a fundamental data structure for storing and manipulating data. Without further ado, let's get started. What's in it for you are, first we will understand what arrays are and how they differ from variables. And next we will see how to declare and initialize an array. Moving further, I will demonstrate how to access elements using indices. Next, most common array operations. After which, the types of array. Once this is done, we will discuss how memory is allocated for arrays. Moving ahead, we will see the properties of arrays. And finally, we will wrap it up the session by looking after the advantages and disadvantages of arrays. First, we will see the basics of C arrays. An array is a linear data structure, meaning that its elements are arranged in a sequential order, that is one after another. Arrays store elements of the same data type, and this homogeneity ensures consistency in data representation. Array elements are stored in adjacent memory locations, ensuring that they are contiguous. This arrangement allows for efficient access and manipulation. Arrays use an index system to access individual elements. The index starts from 0 and goes up to n-1, where n is the size of the array. And this indexing allows for direct and quick access to any element. This convention is widely used in many programming languages like C, C++, Java, and Python. For example, if you have an array with size of 5, the valid indices would be 0, 1, 2, 3, and 4. Accessing an element at index 2 would refer to the third element in the array. The use of zero-based indexing simplifies mathematical calculations and aligns with low-level memory addressing conventions in many programming environments. Now let's break down the code snippet. First, array declaration and initialization. Int numbers 5. This part declares an integer array named numbers with a size of 5. The array is capable of holding 5 integer values. The values within the curly brackets, that is 100, 200, 300, 400, 500, initialize the array with the specified values. Arrays in C use zero-based indexing. In this case, the valid indices for the array numbers are 0, 1, 2, 3, and 4, corresponding to the 5 elements in the array. Int element at 2 equals numbers 2. This line retrieves the value at index 2 of the numbers array. In this specific case, numbers 2 refers to the third element in the array. Remember, indexing starts from 0. Therefore, element at 2 will be assigned the value 300 because numbers 2 corresponds to the element at index 2, which is 300 in the initialized array. So the code initializes an array named numbers with 5 integer elements and then accesses the third element at index 2 and stores its value 300 in the variable element at 2. Arrays in C can be used to store a collection of various data types, including primitive data types like integer, character, float, as well as more complex data types like pointers, structures, and other user-defined types. Arrays can store collection of elements with basic data types like integer, character, float, double, etc. And here is an example. Int array 5 declares an integer array named int array with size of 5. The value within the curly brackets initialize the array with 5 integer values 1, 2, 3, 4, and 5. And next, char array 3 declares the character array named char array with size of 3. The characters A, B, and C are the specific values being assigned to the char array, and these values are enclosed within curly brackets. Similarly, float array 4 declares the floating point array named float array with a size of 4. The array is initialized with the floating point values 1.0, 2.5, 3.7, and 4.2, which is enclosed in the curly brackets. And next, double array 3 declares a double precision floating point array named double array with a size of 3. The array is initialized with 3 double precision floating point values 1.5, 2.8, and 3.2 enclosed in curly brackets. Arrays in C can store collection of derived data types. The given example illustrates the creation of two-dimensional array commonly known as matrix. Int matrix 3, 3 declares a two-dimensional integer array named matrix with dimensions 3 by 3, that is 3 rows and 3 columns. The initialization part 1, 2, 3, 4, 5, 6, 7, 8, and 9 provides the value for each element in the 2D array. Each inner set of curly braces represents a row, and the elements inside those braces represents the values in each column. And the resulting matrix looks like this. You can access individual elements in 2D array using 2 indices. For example, matrix 1, 2 refers to the element in the second row and third column, which is 6 in this case. Arrays in C can store collection of user-defined data types such as structures. Here is an example which illustrates the concept of structure named point. Struct point is a structure definition. So here we define a user-defined data type named point using the struct keyword. This structure contains two members, x and y, both of type int. Struct point points array 2 is an array declaration and initialization. And here we declare an array named points array of type struct point with size of 2. And we initialize the array with two instances of point structure, each containing values for x and y. Each inner set of curly braces represents a separate structure. So the points array 0 is initialized with 1, 2. The first element of points array has x equals 1 and y equals 2. Points array 1 is initialized with 3, 4. The second element of points array has x equals 3 and y equals 4. X represents the horizontal coordinate and y represents the vertical coordinate. So the code is essentially creating and representing 2 points in two-dimensional space, each defined by integer values for x and y coordinates. In C, arrays and pointers have a close relationship. Arrays can act like pointers to their first elements, which makes it easy to manipulate array data using pointer operations. And this connection simplifies the task like passing arrays to the function and dynamically allocating memory. In this code snippet, we declared an array named numbers containing 5 integers, which is initialized with values 10, 20, 30, 40 and 50. Then we declared a pointer variable named ptr. Int asterisk is a type specifier in C, indicating a pointer to an integer. So it denotes a variable that stores the memory address of an integer variable. So the pointer variable is initialized to point the first element of the numbers array. So ptr now points to the memory address of the first element of the numbers array, which allow you to access the elements of the array through pointer manipulation. Now let's understand how arrays differ from variables. Let's start by defining what variables and arrays are. Variables are named storage location in memory that hold a single value of a specific data type, whereas arrays are collections of multiple values of same data type grouped under a single identifier. So variables are used to store individual pieces of data, whereas arrays are used to store multiple related values as a single entity. Arrays allow us to store multiple values of same data type under a single identifier. For example, an array of integers can store a list of numbers, making it convenient to work with collections of data. Arrays are accessed using indices or subscripts, allowing us to retrieve and manipulate individual elements based on their position in the array. On the other hand, variables are accessed directly by their names, providing direct access to the stored value without needing an index. The size of an array is fixed at the time of declaration and determines the number of elements it can hold. However, variable size depends on the data type and platform, allowing for flexibility in storage requirements. Arrays store elements in contiguous memory locations, ensuring efficient memory access and traversal. On the other hand, variables have individual storage locations scattered throughout memory, depending on their declaration and usage. Arrays are commonly used for dealing with collections of data such as lists, matrices, data sets, and more. Variables are ideal for storing individual values or small set of unrelated data, providing flexibility and simplicity in programming. So arrays offer a powerful way to manage collections of related data, while variables provide simplicity and flexibility for storing individual values. And so far we have seen how arrays differ from variables. Now let's understand why do we need an array in data structures. Imagine a scenario where class consists of 10 students and the task at hand is to publish their results. If we were to declare individual variables for each student, managing and manipulating data could quickly become cumbersome. As the class grows or if more students join, the challenge escalates. So declaring and keeping track of individual variables for each student becomes impractical. To overcome this problem, arrays came into the picture. Now let's understand the importance of arrays in programming. Here are several reasons highlighting the importance of arrays in programming. The first reason is data storage. We know that arrays provide a structured and efficient way to store collections of data of same type, and thus makes the programmers to organize the related piece of information under a single variable name so that it makes the code more readable and manageable. And the next reason is random access. Arrays offer constant time access to individual elements through indexing. This feature makes it easy to quickly find specific data without having to go through the entire collection. Next, memory efficiency. Arrays are memory efficient due to their contiguous memory location, meaning that elements in array are stored in adjacent memory locations, which reduce the overhead associated with scattered data storage. And next up we have iteration and traversal. Arrays simplify the process of iterating over elements using loops. This facilitates easy traversal through the entire collection, allowing for efficient data processing and manipulation. And the next reason is mathematical operations. Arrays are well suited for mathematical operations and algorithms, especially in scientific and engineering applications. They provide a natural representation for vectors, matrices, and multidimensional data supporting mathematical computations. And then efficient sorting and searching. Sorting and searching algorithms often rely on array structures. Arrays make algorithms faster by improving searches and sorts. And next reason is data structures implementation. Many fundamental data structures such as stacks, queues, and linked lists can be implemented using arrays. So arrays serve as a building blocks for constructing more complex data structures that are vital in various applications. Moving further, we have compatibility with pointers. In C programming, arrays are closely connected to pointers, making it easy to work with memory operations. And this connection between arrays and pointers enhances the flexibility of arrays in programming. Next up, we have optimized resource usage. Arrays save resources by needing fewer variables. Arrays offer a simple way to handle data, especially with big sets. And finally, we have foundation for algorithms. Many algorithms, ranging from simple sorting algorithms to complex machine learning algorithms, are based on array manipulation. So arrays are crucial for designing algorithms, making computational processes efficient and effective. And these are the reasons that makes an array a fundamental component in developing algorithms, data structures, and a wide range of software applications. Now let's understand array declarations and initializations. Array declaration and initialization in C can be done in several ways. These are the four primary methods for array declaration and initialization in C. First, array declaration only. Next, array initialization with declaration. Then, array initialization with declaration without size. At last, array initialization after declaration using loops. Now we will cover these four different approaches in detail. First up, we have the array declaration. This is a simple way to reserve space for your array without initializing its elements. So here we define the array's name and size without initializing its elements. Look at the syntax. The expression data type, array name, array size is a syntax for declaring an array in C. Data type refers to the data type of the element that the array will hold. It can be any valid C data type such as int, float, char, etc. Array name is the identifier or name given to the array. It is used to refer to the array in the code. Array size. This part indicates the size or number of elements in the array. For example, if you want to declare an integer array named numbers with size of 5, you would use the following syntax. This line of code reserves space for an array of integers called numbers that can store 5 elements. The elements are initially uninitialized and their values may contain garbage data until explicitly assigned. Next, we have array initialization with declaration. Here we initialize an array at the moment of declaration. This is the concise way to set values for your array elements. Here is the general syntax. Data type, array name, array size equals value 1, value 2 up to value n. Data type. This is the data type of the element in the array. In the example, it is int for integers. Array name is the name given to the array. In the example, it is initialized array. Array size. The square brackets indicates the size or number of elements in the array. Value 1, value 2 up to value n. This part is the initialization list enclosed in curly braces. It contains the value that will be assigned to the array elements. In the example, the array is initialized with the values 1, 2, 3, 4 and 5. And this syntax allows you to both declare and initialize an array in a single line of code. Now the array named initialized array is declared with 5 elements and initialized with the values 1, 2, 3, 4 and 5. And next we have the array initialization with declaration without size. Here the compiler automatically determines the size of the array based on the number of elements provided during initialization. And this is the syntax. Data type, array name, the square brackets, the size is left empty, equals value 1, value 2 up to value n. Data type refers to the data type of an element in the array. In this example, it is int for integers. Array name refers to the name given to the array. In this case, it is auto-sized array. Next, empty square brackets. The absence of size within the square brackets indicates that the compiler will automatically determine the size of the array based on the number of elements provided in the initialization list. Value 1, value 2 up to value n is the initialization list enclosed in curly braces. It contains the value that will be assigned to the array elements. In this case, the size of auto-sized array is 5 because there are 5 elements in the initialization list. Lastly, we have the array initialization after declaration using loops. This method allows us to initialize the array elements after declaring it, typically using loops. So in this case, the array is declared first and then initialized using a loop. Here is the formal syntax. First we have declaration part and then we initialize an array using for loop. Now look at an example. Int is the data type of the array elements. Dynamic array is the name of the array. The size of the array is declared as 5. A for loop is used to iterate from 0 to 4 to cover all array indices. The loop runs for each index I from 0 to 4 as specified by I less than 5. Inside the loop, dynamic array I equals I plus 1 is the assignment statement. I plus 1 calculates the dynamic value based on the loop index I. The array element at index I is assigned the value of I plus 1. During each run of the loop, the array element is assigned a value that is 1 more than its index. Now let's see how to access array elements. We can access any element of an array in C using array subscript operator, that is square bracket, and index value I of the element. In C, accessing array element is done using indexes, iterating with loops, and accessing multidimensional arrays. Now let's understand how to access array elements using indexes. This is the general syntax. The two lines are part of the same concept and are used together to declare an array and then access an element within that array. Data type, array name, size. This line is a declaration statement that defines an array named array name. Data type is type of data that the array will store. Example, int, float, char. Array name is name given to the array. Size refers to the number of elements that the array can hold. Now let's see an example. Int myArray5. This declares an integer array named myArray that can store 5 elements. Now data type element equals array name index. This line is used to access an element within the array. Data type, this is the same data type as in the array declaration. Element, this is the variable that will store the value of the accessed array element. Array name, this is the name of the array you want to access. Index, this is the position of the element you want to access within the array. Now the code snippet, int element equals myArray2 accesses the element at index 2. There is third element in myArray which is 30. So the first line declares an array and the second line is an example of how you can access a specific element within that array using the array subscript operator, that is square bracket, and the index. Now let's see an example. This program demonstrates the declaration, initialization, and access of elements in an integer array named myArray. So when you run this program, you will see the output displaying elements at different indexes, including the specific element at index 2. Let's go through the code line by line. Hash include stdio.h. This line includes the standard input-output library stdio.h in your program. It is necessary for using functions like printf and scanf. Int main. This is the beginning of main function, which is the entry point of every C program. Int myArray5. This is declaration part. Here an integer array named myArray is declared. The array has a size of 5, meaning that it can store 5 integers. However, at this point, the values in the array are uninitialized. Next, the initialization part. Here we initialize the array with values. This block initializes each element of myArray with specific values. Now myArray contains the values 10, 20, 30, 40, and 50. Next, we will access and print the array elements using indexes. These lines use printf to display the elements of myArray at different indexes. It prints the values at indexes 0 through 4. This section demonstrates how to access a specific element at index 2 in myArray. The value is stored in the variable element, which is then printed. Finally, return 0. This statement indicates that the program has executed successfully. The main function should return an integer, typically 0 to the operating system to signify successful execution. Now let's execute this program. And you can see the output, which prints the value of an element at index 0 in the myArray. In our case, the value is 10. Similarly, it prints the value of the element at index 1, 2, 3, and 4. At last, it accesses the element at index 2 and it stores in the variable element. Then it prints the value of the element, which is 30. And next, iterating with loops. Loops simplify the iteration process, making it easier to access and manipulate array elements. And here is the syntax. Initialization. This part is where you initialize a variable before entering the loop. Condition is the test condition. When it is true, it allows the loop to continue. Update is the operation that is performed after each iteration of the loop. The loop body contains the statement to be executed inside the loop. In this code snippet, int I equals 0. This is the initialization part. It initializes a variable I to 0 before entering the loop. I less than 5. This is the condition part. The loop continues as long as the condition I less than 5 is true. Plus I. This is update part. It increments the value of I after each iteration of the loop. So this for loop initializes a variable I to 0, continues looping as long as I is less than 5, and increments I by 1 after each iteration. Now let's see an example. This example demonstrates how for loop iterates through the array elements, printing each element along with its index. Hash include stdio.h. This line includes the standard input-output library stdio.h in your program, which is necessary for using functions like printf. Int main. This line marks the beginning of the main function, which is the entry point of every C program. Int myArray5 equals 10, 20, 30, 40, 50. This line declares an integer array named myArray with the size of 5, and it is initialized with the values 10, 20, 30, 40, 50. Next, the for loop. This line starts a for loop. Int I equals 0. This is the initialization part. It initializes a variable I to 0 before entering the loop. I less than 5. This is the condition part. The loop continues as long as the condition I less than 5 is true. Plus I. This is an update part. It increments the value of I after each iteration of the loop. Inside the loop body, this line prints the element at the current index I in myArray using printf. Line 6 marks the end of the for loop. Finally, the return 0. This statement indicates that the program has executed successfully. The main function should return an integer, typically 0 to the operating system, to signify successful execution. Now let's run this code, and you can see the output. The program is using a for loop, which iterates through each index of array from 0 to 4 and prints the corresponding element at that index. So the myArray contains the value 10, 20, 30, 40, 50. And the loop is printing each element along with its index. The output shows the value stored in the array at each index. In next method, we will see how to access elements in two-dimensional array. Here is the syntax. The line 1 is declaration of 2D array. Data type, array name, row size, column size. Data type is type of data that the array will hold. Example, int, float, char. Array name is the name given to the 2D array. Row size and column size, which are the dimensions of the array representing the number of rows and columns respectively. In this example, we declared a 2D array named myMatrix with 3 rows and 4 columns capable of storing integers. However, at this point, the elements of the array are uninitialized, meaning that they contain garbage values. Alternatively, we can use the declaration and initialization in one line. And you can see this line declares and initializes a 2D array named myMatrix. It specifies the values for each element in a row major order. In this case, the array is initialized with specific values. The first row has values 1, 2, 3 and 4. The second row has values 5, 6, 7 and 8. And third row has values 9, 10, 11 and 12. Next, we're going to access a specific element. The line 2 is the syntax. Data type element equals array name, row index, column index. Row index, it specifies the index or position of the desired row in the array. Similarly, column index, it specifies the index or position of the desired column in the array. Element, it is a variable which stores the value of the array element at specified row and column indices. This line accesses the specific element in the array located at row index and column index and assigns its value to the variable element. Look at this example. Int row index equals 1. This line declares an integer variable named row index and assigns the value 1 to it. This variable will be used as an index to specify a particular row in a 2D array. Int column index equals 2. Similarly, this line declares an integer variable named column index and assigns the value 2 to it. This variable will be used as an index to specify a particular column in a 2D array. Int element equals myMatrix row index column index. This line declares an integer variable named element and it gets an element from 2D array named myMatrix at specific row and column and stores it in an integer variable element. Now let's see an example. Hash include stdio.h. This line includes the standard input-output header file, which allows the use of functions like printf and scanf. Int main. This line begins the definition of main function, which is the entry point of C program. This section declares and initializes a 2D array named myMatrix with 3 rows and 3 columns. The array is filled with the values provided in the initialization list. These lines declare two variables, row index and column index, and assigns value to them, which are 1 and 2 respectively. Then it accesses a specific element in my matrix at specified row and column indices and stores it in a variable element. This line prints the value of row index, column index, and element using the printf function. The format specifier %d is used for printing integers. The string element at row %d, column %d, %d, \n is the format string. It contains placeholders indicated by %d, where the values of the corresponding variables will be substituted during printing. The variables row index, column index, and element are supplied as additional arguments to printf. They replace the %d placeholders in the format string. So when the printf statement is executed, it prints a message to the console with the values of row index, column index, and element. Next, the line returns 0. This indicates the end of the main function, and 0 is returned to the operating system, signifying successful program execution. Now let's run this program. Therefore, the output will be element at row 1, column 2 is 6. The message indicates that the value 6 is located at the specified row and column, which is row 1 and column 2 in 2D array my matrix. The row and column indices starts from 0, so row 1 corresponds to the second row and the column 2 corresponds to the third column in zero-based indexing. As I mentioned earlier, zero-based indexing is a numbering system used in programming languages like C. It means that the first element in the sequence, such as an array or other data structures, is assigned the index 0, and the subsequent elements are accessed with incrementally increasing indices. Let's move to the next topic, which is array operations. These are the operations in array. Array operations in C refers to various tasks and manipulations that can be performed on arrays. So what an array can do with the elements inside it is the operation of arrays. The first operation is declaration and initialization. Declaring an array involves specifying its data type and size. Initialization is the process of assigning initial values to the array elements. And here is the syntax. The first line is the declaration of an integer array with size 5. Line 2 is the syntax for declaration and initialization of an integer array. And next operation is accessing elements. Accessing elements refers to retrieving the values stored at specific positions called indices within the array. And this is the syntax. Here we are accessing the element at index 2. Earlier in the video, we have discussed the concept of declaration and initialization, where we create arrays and set their initial values. We also covered accessing elements, demonstrating how to retrieve specific elements within the array. Now let's move on to the next set of operations. Next, updating elements. Updating elements involves modifying the values stored at specific positions called indices within the array. And this is the syntax. Here we are updating the element at index 3. Array 3 equals 10. It represents the operation of updating the element at index 3 in the array. Let's break down the statement. ARR is the name of the array. 3 within the square bracket is the index indicating the position within the array. Equals 10, the assignment operator assigning the value 10 to the element at index 3. This statement is updating the value stored in the array named ARR at the position indexed by 3 to be equal to 10. If the original value at index 3 was, for example, 7, it would be replaced by 10 after this operation. And the next operation is traversal with modification. Traversal involves visiting each element of the array. Traversal with modification implies performing some operation on each element during the traversal. This is the syntax for traversal. Traversal is the simplest form. Here we visit each element of the array. The purpose is often to inspect or operate on each element without modifying them necessarily. The syntax for basic traversal is given here. Traversal with modification. This extends traversal by including an operation that modifies each element during the traversal. In both syntax, I is the loop variable representing the index of the current element. Length is the length of the array. ARRI represents the current element being processed. In both cases, the loop iterates through each element of the array, but in the with modification version, there is an additional step inside the loop that modifies the element. And next operation is finding the length of the array. Finding the length of an array involves determining the number of elements it contains. To find the length of the array, you divide the total size of the array by the size of one element. And this is the syntax. Size of array returns the total size in bytes occupied by the array ARR. This includes all elements of the array. Size of array 0 returns the size in bytes of a single element in the array. The 0 indexing is used to get the size of the first element, since all elements in C array have the same size. Now this part, size of array divided by size of array of 0, divides the total size of the array by size of a single element. The result is the number of elements in the array. Int length declares an integer variable named length and assigns it the result of the division. Now this variable holds the number of elements in the array. Now let's see how to find the length of an array. In C programming, the size of operator is used to determine the size of a data type or a variable in terms of bytes. For example, an array of 10 integers would occupy 20 or 40 bytes depending on whether the compiler is using 32-bit or 64-bit architecture. Similarly, an array of 10 characters would occupy 10 bytes. Now in this case, when you assume that the size of an int is 4 bytes, it means that each element of the array named ARR, which is of type int, takes up 4 bytes of memory. So when you declare int ARR 5, you are essentially setting memory to store 5 integers. And based on the assumption, each integer would occupy 4 bytes. Therefore, the total memory allocated for the array named ARR would be 5 times 4 equals 20 bytes. So size of array is 20 bytes. Since ARR0 is an int and we assumed int as 4 bytes, so size of array 0 is 4 bytes. To find the length of the array, we divide the total size of the array by the size of one element. Therefore, the length of the array is 5 as there are 5 elements in the array. And next operation is sorting. Sorting rearranges the elements of an array in a specific order such as ascending or descending. This facilitates efficient searching and other operations. And here is the syntax. Let's break down the syntax. First, include the header file. This line includes the standard library header file stdlib.h. It is necessary for using the qsort function. And next, the comparison function compare. This is a custom comparison function named compare used by qsort. The function named compare takes two constant void pointers denoted as a and b. Now let's talk about the type constant void pointer which is used in the comparison function compare. In C, void asterisk or void pointer is a generic pointer that can point to any data type. The const qualifier means we can't change the actual information these pointers are referring to. In the compare function, we are saying the pointers a and b are declared as constant void pointers, indicating that they are pointers to data of unknown type and that the data they point to cannot be modified within the scope of the function. And this flexibility makes qsort suitable for sorting arrays of different data types using a single comparison function. In compare function, the typecast to int pointer is used to convert the pointers from constant void pointer to integers. So the typecast int asterisk is converting pointers from pointers to data of unknown type to pointers to integers. What is typecast? Typecasting is also known as type conversion, which is a process of converting a variable from one data type to another. Inside the function, asterisk int asterisk a minus asterisk int asterisk b subtracts the value that a and b points to. This subtraction determines the sorting order. In the expression asterisk int asterisk a, the part asterisk int asterisk is a typecast that treats the value at a as an integer. The outer bracket indicates dereferencing, which retrieves the actual value stored at the memory location pointed to by a. So asterisk int asterisk a means getting the value pointed to by a and treating it as an integer. Similarly, the expression asterisk int asterisk b means treating the value at b as an integer. It involves typecasting the data pointed to by b to be interpreted as an integer, and then the asterisk operator is used to retrieve the value at that memory location. The line qsort ARR length size of int compare is using the qsort function to sort the elements of the array named ARR. Now let's break down the parameters. ARR is the array to be sorted. Length is the number of elements in the array. Size of int, it is the size of each element in the array in bytes. It is provided to inform qsort about the size of each element in the array. Compare is the comparison function that defines the sorting order. So this line of code arranges a specific number of items in the array. It assumes each item is as big as an integer and the actual order is determined by the logic in compare function. The next array operation is searching. Searching for an element in an array can be done using linear search or binary search. Linear search is a straightforward search algorithm that scans through each element in the array one by one until it finds the target value. So it checks each element sequentially until a match is found or until the entire array has been searched. And here is the syntax. Int search int key. This line declares a function named search that takes an integer parameter key. For int I equals 0, I less than length, I plus plus. This line initiates a loop that iterates through the array from index 0 to length minus 1. If ARR I equals key, So inside the loop, this line checks if the current element in the array is equal to the target key. Return I means if a match is found, it returns the index I where the element is found in the array. Return -1. If the loop completes without finding a match, it returns -1 to indicate that the element is not present in the array. So this function performs a linear search through the array, returning the index where the key is found, or -1 if the key is not present in the array. Next, binary search. Binary search is an efficient search algorithm that is applicable to sorted arrays. It works by repeatedly dividing the search range in half until the target value is found. In this syntax, we defined a function named binary search that performs binary search in a sorted array to find a specific key. Int binary search, int key. This line declares a function named binary search that takes an integer parameter key. Int low equals 0, high equals length -1. So in this line, we initialize two variables, low and high, representing the search range. While low less than or equal to high, this line initiates a loop that continues as long as the search range is not empty. Int mid equals low plus high minus low by 2. So this line calculates the middle index of the current search range. If ARR mid equals key, return mid. So these lines checks if the key is equal to middle element. If so, it will return the index where the element is found. If ARR mid is less than key, low equals mid plus 1. So these lines checks if the key is greater than middle element and updates the search range to right half. Else high equals mid minus 1. This line checks if the key is less than the middle element and updates the search range to left half. Return -1. If the loop completes without finding the key, it returns -1 to indicate that the element is not present in the array. So this function performs binary search in a sorted array, returning the index where the key is found, or -1 if the key is not present in the array. And the next operation is copying arrays. It is a process of creating a duplicate of an existing array. This can be done either for entire array or for a specific portion of it. So copying arrays is like making a backup, while you can make changes to the duplicate array without altering the original. So in this syntax, we are creating a copy of the array named ARR using the memcopy function. Int ARR copy length. This line declares a new array named ARR copy with the same length as the original array. The next line, memcopy ARR copy ARR size of ARR uses the memcopy function to copy the content of the original array ARR to the new array ARR copy. The size of ARR ensures that the entire content of the array is copied. After this operation, ARR copy will contain the same element as the original array ARR. And next operation is insertion. Insertion in an array involves adding a new element at a specified position. So when we add a new element to a specific spot in the array, usually means moving some other elements around to make space for it. And this process ensures that the array maintains its order and the new element becomes the part of the sequence. The given syntax inserts a new value into the array at the specified position. The given loop starts from the end of the array and iterates backwards until it reaches the specified position. It shifts element to the right and creates space for new value. Inside the loop, ARR I plus 1 equals ARR I. This expression copies the value of the element at index I in the array to the next position, which is at the index I plus 1. And this line of code is part of a loop that is shifting elements to the right and creating space for the insertion of a new value at the specified position in the array. ARR position equals new value. This expression assigns the new value to the array at the specified position, and this step completes the process of inserting a new element into the array at the desired location. After this operation, the array has a new value inserted at the specified position and the length of the array is increased by 1. And finally, we have deletion operation. Deletion in array involves removing an element from a specified position. When deleting an element from the array, we often need to shift the remaining elements to fill the gap left by the removal to maintain the array's order. The code snippet deletes an element from the array at the specified position. It shifts the remaining element to close the gap created by the removal. The loop begins at the specified position and continues until the element just before the last element in a sequence. Length -1. It shifts each element one position to the left, that is the lower index. So it effectively removes an element at the specified position. Inside the loop, each element is moved one position to the left. So the statement ARRI equals ARRI plus 1 copies the value of the element at next position, which is I plus 1, to the current position I. So it effectively overrides the current element with the value of the next element. Length minus. So after the loop completes, the length of the array is decreased by 1. And thus it indicates that an element has been successfully deleted. After this operation, the element at a specified position is removed from the array and the length of the array is decreased accordingly. Now let's move to the next topic, which is types of array. There are different types of arrays based on their dimensions and element data types. Here are the main types of arrays in C. There are three types of arrays, which are one-dimensional array, two-dimensional array, and multidimensional array. A one-dimensional array is a linear data structure that represents a fixed size sequence of elements. So all elements in the array are of the same data type. The elements are stored in contiguous memory location, meaning that the memory addresses of consecutive elements are consecutive. And each element in the array is identified by a unique index or subscript starting from 0 for the first element. The total number of elements in the array is known as its size or length. Here is a general syntax for declaring a one-dimensional array. Data type, array name, size. And here is an example, int numbers 5. Here we define an integer array named numbers with size of 5. Elements in one-dimensional array are accessed using their index. And the index ranges from 0 to size minus 1. The memory for one-dimensional array is allocated consecutively. The address of the first element represents the base address of the array. So one-dimensional array provides a way to store and manipulate collections of elements of same data type in a contiguous memory location, with each element accessible through a unique index. Here is an example of one-dimensional array. In this example, int arr5 declares an integer array named arr with size of 5, and we initialize the array with the values, which are 10, 20, 30, 40, and 50. A for loop is used to iterate through the array, and each element is printed with its index, and you can see the output. Now let's understand the two-dimensional array. In two-dimensional array, elements are arranged in rows and columns. The array can be visualized as a grid where each cell holds an element. All elements in the two-dimensional array are of same data type. In two-dimensional array, we access elements using two indices, one for row and another for column. This is the general syntax for declaring a two-dimensional array. Data type, array name, rows, columns. And here is an example, int matrix 3, 4. Here we defined a two-dimensional array named matrix with 3 rows and 4 columns. Int indicates the data type that the array will store integers. Matrix is the array name. 3 and 4 inside the square bracket indicates the size of the array, which signifies that the array has 3 rows and 4 columns. So an array named matrix is a two-dimensional array that can hold a total of 3 times 4 equals 12 integer elements. As I mentioned earlier, elements in two-dimensional array are accessed using two indices, one for row and another for column. Indices starts from 0, so the first element is at position 0, 0. Memory for two-dimensional array is allocated consecutively with elements organized row by row. The base address of the array corresponds to the memory location of the element at 0, 0. So a two-dimensional array provides a way to organize data in a grid-like structure, allowing for the representation of tables and matrices. It is a useful tool in C programming for handling two-dimensional datasets. Here is an example for two-dimensional array. First, we included the standard input-output library stdio.h, which is necessary for using the functions like printf for output. Int main, which declares the main function, which is the starting point for C program. This section declares and initializes a 2D array named matrix. It has 3 rows and 4 columns. The provided values initialize the element of the array in row-wise fashion. These lines demonstrates how to access specific element in the 2D array. Matrix 0, 1 refers to the element in the first row and second column, while matrix 2, 3 refers to the element in the third row and fourth column. These lines use printf to display the values of value 1 and value 2 on the console. The format specifier %d is used for integers. Return 0 indicates the end of the main function and end of the program. So the return 0 statement signifies a successful execution of a program. Now let's execute this program. And you can see in the output, value 1 is assigned the value of matrix 0, 1, which is the element at first row and second column, which is 2. Value 2 is assigned the value of matrix 2, 3, which is the element at third row and fourth column, which is 12. The printf statements then display these values on the console. And these are the examples of multidimensional arrays with dimensions ranging from 3 to 6. A three-dimensional array is a data structure that represents a fixed size sequence of elements organized in 3 dimensions, which are layers, rows, and columns. Int space 3, 4, 5 represents a three-dimensional array named space with 3 layers, each containing 4 rows and 5 columns. A 4-dimensional array is a data structure that extends the concept of 3-dimensional array into an additional dimension. It organizes elements in 4 dimensions. Each is identified by a unique set of indices such as layers, sublayers, rows, and columns. Int hypercube 2345 represents a 4-dimensional array named hypercube with 2 hyperspace layers. Within each hyperspace layer, there are 3 layers. Within each layer, there are 4 rows. Within each row, there are 5 columns. A 5-dimensional array is a data structure that further extends the concept of multidimensional array by organizing elements in 5 dimensions. It includes layers, sublayers, rows, columns, and an additional property dimension. The array int pentatope 23456 represents a 5-dimensional array named pentatope. It has 2 properties. Within each property, there are 3 layers. Within each layer, there are 4 rows. Within each row, there are 5 columns. Within each column, there are 6 elements. A 6-dimensional array is a data structure that goes beyond the 5-dimensional array, introducing an additional dimension to organize elements. The array int hexadecimal 234567 represents a 6-dimensional array named hexadecimal. It has 2 properties. Within each property, there are 3 layers. Within each layer, there are 4 rows. Within each row, there are 5 columns. Within each column, there are 6 elements. And additionally, there is an extra dimension with 7 units. Now let's understand how memory is allocated for arrays. Array memory allocation is the act of reserving a continuous chunk of memory to hold the elements of an array. And these are the primary types of array memory allocation: static allocation, memory footprint of arrays, dynamic allocation, releasing memory. In static array allocation, memory is allocated at compile time. Static arrays have a fixed size determined at compile time, and memory is reserved on the stack. So the static arrays have a fixed size that cannot be altered while the program is running, which makes them suitable when array size is predetermined. Here is an example. Here we declared a static array named static array with a fixed size of 5, and the memory for this array is allocated during the compilation of the program. Next, dynamic memory allocation. In dynamic allocation, memory is allocated at runtime. For example, in languages like C++, we use the new keyword to dynamically allocate an array. In Python, you can use a list to dynamically allocate an array. If you are working with numerical data in Python, use NumPy arrays. NumPy provides efficient array operation and memory management. Now coming back to dynamic allocation in C, the size and type of the array can be determined during the execution of the program, which enable flexibility in adjusting the array size as needed. The process of dynamically allocating memory is accomplished using the functions like malloc, calloc, or realloc. The memory allocated by these functions is usually reserved on the heap. And here is an example. In this example, you are dynamically allocating memory on the heap for an array of 5 integers. Now breaking down the code, malloc 5 asterisk size of int. This part requests memory on the heap to store an array of 5 integers. The size of int is used to determine the size of one integer in bytes. The total allocated memory is 5 times the size of an integer. Int asterisk. This part is typecast. It explicitly converts the void pointer written by the malloc to the pointer of type integer pointer, indicating that the memory being allocated is intended to store integers. Int asterisk dynamic array equals. This line declares a pointer named dynamic array and assigns the address of the newly allocated memory block. So after this line, dynamic array points to a block of memory on the heap that can hold 5 integers. Remember, when you are done using this dynamically allocated memory, it is important to free it using the free function to prevent memory leaks. For example, free dynamic array, this statement is crucial for releasing dynamically allocated memory. So when you call this function, it tells the operating system that you are done using the memory block pointed to by dynamic array, and the system can reclaim that memory for future use. By releasing memory with free, you can ensure that your program uses memory efficiently by returning the unused memory to the system for other processes or future allocations. We have 4 library functions defined under stdlib.h header file, which can be used to dynamically allocate memory, which are malloc, calloc, free, realloc. Malloc allocates memory dynamically on the heap. It is commonly used to allocate memory for the arrays when the size of the array is not known at compile time. The allocated memory is typically accessed using pointers. And here is an example. I already explained this example. So this function is essential for dynamic memory allocation, especially when you are dealing with arrays whose sizes are determined during the program execution rather than compile time. The next function is calloc. Calloc dynamically allocates memory on the heap similar to malloc. Unlike malloc, calloc initializes the allocated memory to 0. So calloc is handy when you want memory to start with a specific value like 0. So in this example, we are setting up a pointer array to refer a block of memory capable of storing 5 integers. with each element initialized to 0. And next we have realloc. It resizes previously allocated memory blocks. So it is commonly used in a scenario where the size of an array is need to be adjusted dynamically. And here is an example. This line of code modifies the memory block that array points to so that it is large enough to hold 10 integers. After this modification, now array points to newly adjusted memory block. Next function is free. Free function is used to deallocate memory that was previously allocated dynamically. As I mentioned earlier, it is essential for managing memory usage and preventing memory leaks. So when you allocate memory dynamically using malloc, calloc or realloc, it is important to free that memory when it is no longer needed. And it is done using this function. Here is an example. This line ensures that the memory allocated for the array pointed to by array is released. And next, memory footprint of arrays. The amount of memory occupied by an array is called memory footprint of arrays. Both static and dynamic arrays have a memory footprint. Static arrays have a fixed memory footprint determined at compile time, while dynamic arrays have a footprint that can be adjusted during the runtime based on the actual size of the array. The memory footprint of an array is determined by multiplying the number of elements by the size of each element in bytes. For example, if you have an array of 10 integers and each integer is 4 bytes, so the total memory footprint is 10 times 4 equals 40 bytes. Note that different data types have different sizes. For example, an integer might have 4 bytes, a float might be 4 bytes, and double might be 8 bytes. And finally, we have releasing memory. It refers to the process of deallocating or freeing memory that was previously allocated dynamically during program execution. Typically, this was done using free function. So in this example, free array deallocates the memory previously allocated for the array, ensuring that it is available for reuse. And note that set the pointer to null after freeing the memory. It is a good practice to avoid dangling pointers. Dangling pointers are the pointers that still point to the memory location that have been deallocated, which leads to undefined behavior if dereferenced. Now let's see an example which demonstrates dynamic memory allocation and reallocation using malloc, calloc, and realloc. It also includes a function free memory to safely free the allocated memory. Enter the size of the array. Here the array is allocated using malloc, in which we initialize with odd values starting from 1, and it is incremented by 2 for each element. And this results in the array 1, 3, 5, 7, 9, 11. And next the array is allocated using calloc, which is initialized with even values starting from 0, and it is incremented by 2 for each element. And this results in the array 0, 2, 4, 6, 8, 10. After reallocating memory for the array allocated with malloc, the additional elements are initialized with odd values starting from 13 and incremented by 2 for each element. And thus results in the array 1, 3, 5, 7, 9, 11, 13, 15, 17, 19 and 21. And now let's move to the properties of arrays. And these are the properties of arrays in C. Arrays in C have a fixed size. It means once you define the size of the array, then it cannot be changed during the runtime. So the size must be specified at compile time. The elements of an array in C are stored in contiguous memory location, which means the memory address of successive elements are adjacent. Next, zero-based indexing, which means array indexing in C starts from 0. The first element starts with index 0 and second element with 1 and so on. And next we have homogeneous data type. Arrays in C store data of the same data type. So all elements must have a same data type, which is determined at the time of declaration. Direct memory access. Elements in an array can be accessed directly using their index, which allow for efficient and random access to array elements. Arrays in C are essentially pointers to the first element. With pointer arithmetic, you can traverse through the elements of the array. The size of an array in bytes can be found using the size of operator. It calculates the size of one element and it multiplies it by the number of the elements in the array. And now let's see the advantages and disadvantages of array. Arrays provide direct access to elements using their index, which allow for quick retrieval and modification of individual elements. Using arrays, you can store a multiple element of same data type in a single contiguous block of memory. So this results in a compact representation and efficient memory usage. Traversing through the array is straightforward using a single loop, and this simplicity in traversal is due to the sequential layout of elements in memory, and thus it makes easy to iterate over the array and perform operations on each element. Arrays simplify sorting operation because it is easy to implement various sorting algorithm with fewer lines of code. Sorting algorithms like bubble sort, selection sort, or even the efficient ones like quicksort or medsort can be applied directly to the arrays because of their random access and sequential layout property. Talking about the disadvantages, it is fixed size. Arrays in C requires a fixed size which is to be declared at compile time. This fixed size cannot be changed dynamically during the program execution. So this limitation restricts the flexibility of array and makes them unsuitable for the scenario where the number of elements may vary at runtime. Insertion and deletion operation in arrays can be inefficient and costly, especially when elements need to be rearranged. And that's all for this session. Thank you so much for watching.